from one weight to the next. Your body weight is continuous, much like the weather. So even if it's 50 degrees out today and it's 30 degrees out tomorrow, from today to tomorrow, it had to go from 50 to 30, touching every number in between. So did he weigh 120 or 108.625? All of those answers are yes. He had to take on every weight or every value. So he had to take on every weight value between 90 and 150. And again, because weight is that key word we keep hearing, which is continuous. He had to take on every weight because weight is continuous, much like the weather and age. So we could use this also with our theorem of Ivt. So Ivt is applicable because we know that he went from every weight to 90 to 150. So if you think back, Ivt says that you are guaranteed a value from the min max to the from the min to the max, basically. So if he was 90 and then he was 150 from those two ages or birthdays, then we are guaranteed on the interval 10 to 17 that he weighed exactly any weight from 90 to 150. And that guarantee is given to me by Ivt. We're not guaranteed that he was ever less or more. We're just guaranteed that he was between. So again, just going back and reflecting on old theorems. So Ivt basically would guarantee that somewhere from his 10th to 17th birthday, he weighed any weight from 90 to 150. So that's kind of the summary of Ivt. A question or example relating back to that would be that a function h is continuous on a closed interval where h of negative 2 is 0 and h of 11 is negative 20. Is there a guaranteed value c on that interval from negative 2 to 11 such that h of c equals negative 17? Justify your answer. So my justification comes in two ways. We start by saying yes or no. So if you look at those two values, negative 2 to 11 are my x's. My y's are 0 to negative 20. So is negative 17 in that range? Yes, it is. So I would say yes, since h is continuous, and that's the key phrase, from negative 2 to 11, then h of c equals negative 17 at some c, because h of negative 2 equals 0 and h of 11 equals negative 20. So to get your credit or your points for your justification, you would have to have the beginning and the end, as well as the word continuous, you could have said something else along the lines of that h of 11 equals negative 20 is less than h of c, which is less than h of negative 2, which equals 0 as well. So I've seen these answers given as intervals also. So you could do it as an interval, you can do it as a sentence, but as long as you, again, you see I have on that page the negative 11 and the negative 2 and what they're equal to. The last thing you would need to put is, how do you know this? Why do you know this? We know this by IVT. Okay, does function f, where f of x equals 2x squared minus 3x minus 1, have a real root on the open interval? So what represents a real root? A real root represents a value at which f of x would equal 0. So in order to show that f of x could equal 0, you have to show f of 2 and f of 1. So f of 2 is 9 and f of 1 is negative 2. So because 0 is between negative 2 and 9, same idea. We know that f is continuous because it's a polynomial. So we can say, since f of x is continuous and f of 2 equals 9 and f of 1 equals negative 2. 0 is between 9 and negative 2. By IVT, f of x has a real root between 1 and 2. So everybody okay with IVT? So again, IVT, EVT, MVT, we kind of take like a summary quiz on all of those and their applications because they're the three most commonly mixed up theorems in calc because they're so closely related, but they prove such different things. So the key part about IVT, what didn't I use in either of these last two examples? What didn't I use, Maddie? A derivative. IVT is like the only calculus theorem that you do not need a derivative to prove. IVT is the only calculus theorem you do not need a derivative to prove. Okay, EVT, on the other hand, uses the application of a derivative. So EVT says a continuous. Man, that's such a key word. Function f of x on closed interval AB has both a max and a min. EVT guarantees a max and a min on the original function as long as it is a closed interval. So in these examples, it says for the functions below, identify the max and the min. So these are closed intervals. They're continuous. So in the case of this example here, this point down there would be my minimum. So I need a min at x equals -1. My max is at the peak of the parabola. So my max is at x equals 1. And again, if you didn't put the x equals, but you put a min or a max, then you would list it as the y values. So you could have also said a max at 3, but if you put 3, you're implying the y. If you have the x equals, you're obviously giving the x value. So you just have to be careful about how you write it or how you read your answers. So if you put at 3, you're not saying 3 on x, you're saying 3 on y. In the second example, my key points or points of concern are my endpoints as well as my vertex. Now, my endpoints both are at the same height. So if my endpoints are at the same height, what theorem could I use on example G? My endpoints are at the same height. What theorem could I use? There's a theorem that's very particular about your heights needing to be the same. Rolle's, thank you. So we could use Rolle's theorem for this example. Could I use Rolle's theorem in example A? No, because the beginning and the end points are different heights. Therefore, I cannot use Rolle's. We could, however, use it in example B. In example B, you could say you have a max at both endpoints, or simply list the y value of 2. So you could make that connection in number 2 to an IVT. You could also say on the interval -1 to 3, I am guaranteed any value from -2 to 2. So the connection to all the theorems kind of comes into play. So in example C, is that continuous? If I have closed intervals and continuous, what happens to the min and the max in this problem then? The min and the max both end up being at the same y value. So a constant function that is on a closed interval is the only case in which you can have an absolute min and an absolute max at the exact same value. Okay? So I believe the next part of your note packet looks like this. You have the mean value theorem. Yeah? This is actually a really nice interpretation of the mean value theorem. This is a more visual interpretation than what we looked at yesterday. So yesterday I gave you a visual, but we didn't actually interpret it or work through it. So what we're going to do in this example is actually work through the visual. So we are given if f is continuous on a closed interval AB and differentiable on the open interval AB, then there always exists a number c such that the derivative equals the slope of the secant. So we are guaranteed a tangent line equals a secant line at some point. It kind of relates to IVT in the sense that you're guaranteed to weigh every value. In the figure on the right, label the indicated ordered pairs. So first we want to label a segment whose length is f of b minus f of a. So in our diagram, we're given a curve and we're given AB. So that makes this point here the coordinates a, f of a, which makes this point's coordinates b, f of b. So we are asked to label and draw a segment whose length would be f of b minus f of a. So how could you draw or label a segment whose length is f of b minus f of a? What does that really represent? Do you agree that if I drew in that triangle from this point to this point, that would be f of b minus f of a? And from here to there would represent the distance b minus a. What would this quotient represent then? Well, that quotient, can't you see, ends up being rise over run? The quotient ends up being rise over run. What you go up and down versus what you go over. So if it's rise over run, what's the fancy math term for that? Slope. So the quotient f of b minus f of a is the slope of the segment joining the 2 points. Draw that. Pick a point C between A and B. Your point C doesn't have to match my point C, which doesn't have to match your point C, which doesn't have to match their point C. So I might make my C value close to A. You might make your C value close to B. Those of us that are like me and like symmetry might put it right smack in the middle. F prime of C gives what? F prime of C gives the slope of the line. We know that based on the definition of the derivative. The derivative is a rate of change. The derivative at a point represents the slope of that point to what? F prime of C gives the slope of the line blank to the curve. What word do you think is going to go in there? It's the calc word we use all the time. What'd you say? It's tangent, yeah. So f prime of C gives the slope of the line tangent to the curve f of x at the point But what would that point be on my curve? Go ahead, Bethany. Perfect. It's C, f of C. On the graph above, locate the C value that is guaranteed by the mean value theorem. So we put our C values on there. Now what we need to do is draw a line tangent to that curve. So what you're trying to do is draw a line that kind of represents the slope of that curve. Maybe not perfectly perfect, but what do those two lines kind of look like they could be to each other? They should look kind of parallel if you drew your lines on straight enough. So mean value theorem can be restated from the previous statement at the top to say that this will create two parallel lines, one through A, f of A, and B, f of B. And the other, where? Exactly.